Alright, class. Today we are going to imagine you are standing in front of a big fan and feeling the air blow on your face. It feels cool, right? That is because moving air takes heat away from your skin faster than still air. This simple idea is what we call external forced convection, and it happens everywhere, in cars, airplanes, power plants, and even when you are outside on a windy day. Let's make it super easy. Imagine when air or water flows over something, like a car or a building, it makes two things happen. It pushes on the object, which we call drag, and it takes away heat, which is cooling. Today we'll learn how engineers predict how much push or drag happens and how fast things cool down when air flows over them. Now, when something is surrounded by air, the air far away moves fast, but right near the surface, the air slows down. The very first layer of air sticks to the object like glue and doesn't move at all. This is called the no-slip condition. Because of this, air forms something like a fuzzy blanket called the boundary layer. Inside this layer, air starts from zero speed and slowly speeds up as you move away from the surface until it reaches the free stream speed, which is the fast speed far away. This also happens to temperature. Right near a hot surface, air is hot, but it cools down as you go farther from the surface. These two things, the velocity layer and thermal layer, are the key to understanding external forced convection. When air flows over objects like cars or planes, it causes drag. This drag happens in two ways. First, because air sticks to the object, it causes friction, which slows things down. This is called friction drag. Second, the shape of the object makes air pile up in the front and form low pressure in the back, which pulls it backwards. This is called pressure drag. So, if you put your hand outside a moving car, you feel both the friction and the push from air pressure. Now, engineers love to make things simple by using something called the drag coefficient. It's like a magic number that tells you how hard the air is pushing on the object. If you make your hand flat facing the wind, it has a high drag coefficient. But if you tilt your hand, like slicing through the air, the drag is much less. Next, let's talk about cooling. When hot objects, like engine surfaces or hot pipes, are surrounded by air, they lose heat by convection. We measure how fast they cool by something called the heat transfer coefficient, and we use a shortcut called the Nusselt number to make it easier to calculate. The Nusselt number basically tells you how powerful the heat transfer is compared to simple conduction. Bigger Nusselt numbers mean faster cooling. For flat plates, like car windows, when air flows from one end to the other, the flow starts nice and smooth, called laminar flow, but after some distance, it gets messy and swirly, called turbulent flow. Laminar flow has smaller drag and slower heat transfer, while turbulent flow has bigger drag and faster heat transfer. So, engineers have found easy equations to figure out drag and cooling by looking at something called the Reynolds number, which is like a traffic meter telling you how fast and how big the flow is. But not everything is flat. Sometimes we have cylinders, like poles, or spheres, like balls. When air flows over these shapes, the flow wraps around the front but separates at the back, making a swirling wake like a boat behind a ship. This separation causes more drag. For cylinders and spheres, most of the drag comes from pressure drag, not friction drag. Engineers use special graphs to quickly see how drag changes based on flow speed. When we have many tubes together, like in a power plant's heat exchanger, air flows around many pipes. This is called tube banks. Sometimes the tubes are lined up neatly, sometimes they are staggered like bricks. Staggered tubes make the air swirl more, which means more cooling, but also more drag. Finally, engineers also look at things like unheated starting lengths, where only part of the surface is hot. This changes how quickly the thermal boundary layer grows. They also check for cases where the surface itself is moving, like in manufacturing lines where sheets of material are moving while being cooled by air. So to wrap up, external forced convection is all about how air pushes and cools things from the outside. Engineers use smart shortcuts like drag coefficients, Nusselt numbers, and Reynolds numbers to quickly figure out how much force and cooling happens. Every time you feel wind on your face, or see a fan cooling something, or watch a flag fluttering, you are actually seeing the magic of external forced convection in action.